Should we start? Okay. Hi everyone. I am Shivji, and I will be talking about how to use Postgres for analytics. Let's go around the story. First of all, the views and opinions that I present here are my own and do not represent my employer's. So this is kind of a smaller room, but if you want to get the slides, so you can look at some smaller parts and stuff. You can scan the QR. Maybe in this room it's not required. I'll first go through some background to lay context. I'll leave you with some questions, right? Hopefully I can hold your attention and come back and we can have a sense of the answers for those questions. We did extensive benchmarks because the topic is such to get more insights, configurations, and see where exactly the problems could be. Then I have been working extensively on running analytics databases as part of my day job. So I will bring some notes from there to say what is a good analytics DB. If you had to write one in 2025, for instance, then what are the features that should be there for it to be really performant and the one that has enough features for you to use. And then finally, we will explore some ideas about how can we extend Postgres to get those features, right? This is most about, first we go through benchmarks, see how to tune and stuff, and at the end towards the extending Postgres section, I'll go quickly touching on wider array of things, not deeper, but I am happy to sort of talk to you after the talk in the Q&A or later. So this is very quickly about me. I talked about me already, so I'll probably skip most parts, but areas of interest are databases and distributed systems in general. I used to be a contributor to MySQL replication. A lot of those patches are in open source database today. Used to also be a contributor to Apache Pulsar, which is something very similar to Apache Kafka, if you know that. And right now I work with people, guiding them on contributions on Druid and ClickHouse, which are analytics databases. So when I said earlier that I will bring some notes, those are mostly inspired by what I know about Druid and ClickHouse internals. Here I'll mostly talk about some of the ClickHouse data structures, indexes and stuff. And see how we can do those in Postgres. So let's first look at Postgres and some other databases, not really exactly similar databases, but some other databases, right? I have been attending some talks and I think you would have seen these slides. If not somewhere else, maybe in Peter's slide, the keynote, it was there. So the red ones, the blue one, that is all Stack Overflow survey. You see, in the last 3 years, Postgres has always been on top, so it's obviously very popular. Maybe you know that because you are here having spent some amount already. Right? So then you look at DB engine rankings for database management system of the year, and you see in the last 8 years, Postgres has been there, the database of the year 4 times. Interesting thing, in the last 4 years though, 3 times in the green ink you see Snowflake. So obviously, you can draw a conclusion now that people are really interested in doing analytics on their databases. Now probably even more after the ChatGPT moment and AI and whatnot, right? But then when I sent this slide out for some of my mentors and friends to review, everyone was like, oh, but then Postgres is for OLTP. Why are you even using it for OLAP, right? And these are my answers. So I stick in a slide saying, you know, if you look at the applications, right, if you are a small startup, you typically have some request for analytics much before you have a dedicated analytics stack, right? Most of this talk is not for somebody who is already running a Snowflake or ClickHouse or a Redshift. In terms of the use case, in terms of the internals, obviously you can carry a lot of stuff there and make those work better for you. But we are trying to look here at the persona where somebody, I mean, let's say you are a small startup, you have your Postgres and a bunch of apps, everything is working good. One fine day, the PM suddenly comes up and he wants to know some information, right? You don't go and move the whole data via an ETL to an analytics store and answer the analytics queries. You just go to Postgres and ask for data, right? Just the business use case. So you got to do it. And Postgres is already there in the stack. The data is there. So more gravity, right? Postgres, of course, can do some analytics, but the default Postgres with its default settings obviously is built for people who use it for OLTP, right? So how can we tune it to make it look better for analytics? Indexing, no prices for guessing that. But here what we try to do is, can we stretch Postgres even more to delay the decision of I need an analytics stack now, right? Can we delay that decision, right? And in my opinion, I think if you Google this phrase, there are a lot of people who have written blogs. This is a podcast where there is again talk about Postgres being the Swiss Army knife of databases. Basically, obviously, Postgres does quite well for transactional use cases, but now Postgres has this amazing execution engine where it is able to do things that other databases do really well. And if you look at the 80-20 rule, maybe 20% of those features are there and they can power 80% of the use cases, right? So for example, Oracle used to be, I started working a decade ago, the gold standard for RDBMS. Now Postgres is actually taking off, right? And most of you in this audience would probably trust me on that. MongoDB, I was working in MySQL from 2012 to 15 as a committer, and I mean, MongoDB had just come out and it was all the rage. The new query in the blog obviously was very popular, and JSON data type was something that people absolutely loved about it. Postgres now has JSONB, right? Which does pretty well. I have myself used it in an application, and it was there in production for a couple of years before I sort of left that place. So it does take you quite far. And then how can you not talk about AI these days, right? So I picked up an example just to prove a point, saying, now we just had the ChatGPT moment where AI got very easy to use for most people. And then there are vector databases today which allow you to make certain kinds of index on vector data types and run similarity search indexes. So you have a couple of algorithms for similarity search there as well. And then there are a lot of extensions and forks. So since morning I have seen a lot of talks around extensions and whatnot. So I assume you already mostly know about that. Citus, you can use that for distributing Postgres over a cluster. Timescale for time series. Greenplum is for OLAP. It's a fork. But yeah, I mean, I've been talking a lot of stuff. Let me show you some numbers, right? But obviously all benchmarks are lies. No prices for guessing. I mean, if a certain vendor publishes a benchmark, who wins that benchmark? Come on, right? So, but having said that, everyone has a favorite benchmark tool, and it's obviously important. It's not the only decision maker in your selection of database, but it is a huge factor. There are other things, obviously, ease of use, cost, how much can it do on a given hardware performance. So take whatever I present in the benchmark section with a grain of salt, right? For the benchmarks I did for this talk and trying to explore this idea for last 2 to 3 months, I used ClickBench. I really like ClickBench, right? ClickBench was built by ClickHouse. I use ClickHouse a lot, so I had been using this, extended the same tool. And obviously ClickHouse shows itself as something that is really fast analytics, and they used to be on the top in the ClickBench benchmarks. And along with that, you used to see earlier that other analytics databases would also be near the top, right? And Postgres was somewhere a bit later, which you would expect, right? It's not a dedicated analytics database. Unless you tune it properly, it'll do worse. If you tune it better, it'll obviously come up in the rankings. And by the way, the popularity of Postgres was there as well. You have a bunch of 12 to 15 Postgres compatible databases that are there in the benchmark. The benchmark code is open source. I have myself put PRs, my friends have put PRs and stuff to improve Postgres there. But look at this, right? Like, I mean, if you compare, I mean, this is not exactly apples to apples, obviously. I don't know the exact size of Snowflake XS, but I care more about Postgres here. But I just clicked a bunch of buttons here, and that tells me on the benchmark that Postgres analytics is 55 times worse than Snowflake. I was like, no, I don't like that, right? Right. So let's go in the sort of benchmark scripts and try to see what can we do, right? I mean, somebody obviously took Postgres and put it there, and then in the community style, other people who are better at tuning that can come and tune that. So somebody else in the community went ahead and so, you know what, that's not fair. You should actually make the right indexes, right configs and stuff. And then obviously it makes more sense for the Postgres lovers, right? 3 times worse for analytics than Snowflake, which is great because Snowflake doesn't do transactional, right? So this is good, right? Now we are just 3 times worse. And how did we get there? Again, indexes, right? There are a lot of indexes there because in the benchmark we have 42 analytics style queries, and we wanted to make sure that, you know, the indexes are there to make sure that every query runs faster, and there is a geometric mean then that happens to rank the database, which is a terrible idea, by the way. You shouldn't be ranking databases just like that. Your use case could be different. This queries could be very different. But then there are a bunch of configurations saying, you know what, if the other database is given more memory, then why not shared buffer also have 8 GB for this, then parallel workers for your queries across queries, and you increase wall size and whatnot, right? Can you read these things? I think you can read. I can't read from the side properly. So, but that's okay. I remember the content. So now this is, you don't have to go through the whole thing. This is indicative that you have a lot of indexes, and it doesn't come for free, obviously, right? The total size of indexes here is 36 GB, and it's just 70 GB of data, right? Obviously, you choose the indexes you absolutely need depending on the queries that you have, because it will also affect your write throughput, right? Now you would ask, so these are things that a lot of other people in the community are doing there to make Postgres rank better there. Me and my friends, we sat together, we are doing this project for last 2-3 months, and we did some more optimization, alignment of columns properly and all of those, and this was really accepted well by them, and the PRs were merged quickly. We could improve the insert time for the analytics style ingest, which is basically also reducing table size because of padding. I said indexing time improved, query time improved by 10%. So yeah, I mean, we could contribute a bit, and we continue to sort of work on this. Now, right, let's put in one more database here, right, for comparison, and I'll talk of a lot of database. Some I will just touch a bit, some I'll go a bit deeper to screen the concept. You put DuckDB in here, right? How many of you have heard of DuckDB? Oh, wow, it's popular, right? So now DuckDB seems like even better than Snowflake. Snowflake is the one we saw in DB engines. It's really popular. DBNS of the year 3 times out of last 4, right? So why? One thing you see in memory there, that is one hint. But I would like to leave you with some questions here, so we can go through some theory and sort of map it back to answering these questions. But remember this, that DuckDB did really well, right? And these are a bunch of databases which are a mix of Postgres and DuckDB. Basically what you do is you take the in-memory engine of DuckDB and slap it inside the Postgres extension and have an intelligent way to figure out where the query should go. Then you do analytics much better. So these databases are nothing but Postgres plus a Postgres extension with DuckDB's execution. Why? We will answer that again, right? Again, look at ClickHouse. On the top, the smallest bar means fastest. So ClickHouse, by the way, is way faster than all of these, right? And I'll show one reason why. And we will come back to look at these databases one or two slides max. So like I said earlier, I think I have laid context, right? Let's get into the heart of the talk. The idea again is how we can bridge the gap between Postgres and dedicated analytics databases. So let's go to the heart of the talk. What features would I look for in analytics database in 2025? Columnar storage, right? How many of you understand columnar storage, columnar databases? Have you used those? And a few. So in the interest of everyone, I'll quickly explain those. I have color coded these things so I can explain very quickly. So this is you guys use Postgres, I think. So you understand row-based databases. What you do is you have this whole green patch. This is column number 0. So we put all the values in that row, then the values in the next row, and then the values in the next row. This is my disk. So contiguous locations, the rows are there. In the columnar representation of the same table, you see that this column is marked green. That whole green patch, which is all the values in that column for all the rows, are together. Then all the names are together. You get the idea, right? Analytics queries, by the way, are centered around accessing a lot of data, running some aggregation on those and stuff like that. Now you would imagine if I had to draw an average of the salaries in my organization, and by the way, I'm trying to be humble, my salary is least here. Then you want to fetch all the salaries are in contiguous locations on the disk. It will be faster for me to fetch that. And by the way, columnar representation of data lends itself to very nice compressions, right? One example, if you have a huge column, let's say the value 100 is spread across 1000 times, you can just say 1 spread across 1000 times, not write the whole thing. That's run length encoding for you. And there are a lot of other things, because the same data type is there for a longer period, you can leverage that, right? Parquet is a very popular, permissive, widely adopted, and it's under Apache Foundation, so you can use it safely, right? And it's interoperable with a lot of other databases and engines. But look at the contrast. This is row-based storage, and this is column-based storage. So 5 times less, right? Postgres would also take something around 70 GB. This is CSV, TSV, and the last is JSON. Anyone wants to take a guess why JSON is so big? Yes, just wanted to check if people are sleeping, so I stick that in, right? So now that was just columnar file representation. We talk of the databases. These are all columnar databases in the red box. 13 to 14 GB mostly. Postgres is 72 GB. Postgres tuned with all the indexes, everything is around 120 GB, right? While we reduce the query latency, we did that for storage trade-offs and maybe some write throughput because you have a lot of indexes. So all these databases that query data kept in Parquet format on the disk, they take very less space. Snowflake, you see, it's amazing, right? Less than 12 GB. And these are huge data sets. That's what analytics is built for. So this really matters. So now again, talking of Parquet, right? I have mostly covered the sort of things about Parquet a bit already. It's optimized for direct querying and can read specific columns only. You don't have to stream everything in the memory and all of that. I'll just explain that more. But look at this, right? This is a case study that I could find in AWS blogs. It's one of the fastest growing data types in Amazon S3. Amazon S3 obviously has a huge amount of data by now. Anyone here who has not used S3? Okay, good. So I can stay on the Parquet level and above. So and AWS handles 15 million plus requests per second on Parquet data, and there are exabytes of Parquet data and all of that. Means Parquet is heavily used. So we did number 1 feature. Number 2 feature that we want to do is vectorized execution. Now I was in one of the previous talks that Amit had done, and I absolutely loved it because he goes much deeper. I could learn a lot. How many of you attended that talk? Okay, so you guys probably know this already. I don't know Postgres internal so much, so I stick in some pictures to save me. But what I'm trying to do is vectorized execution will try to use SIMD, single instruction, multiple data. So you have a bunch of CPU cores. If you go to one instance of the processing unit, for one instruction, it can execute a lot of pieces of data. So you take a batch or a vector of data. A column, let's say, has 1000 rows. This is small by analytic standards, but you can take 100 of them, and one CPU instruction can execute a filter or something on all of this data, right? I'll explain it further, right? But basically consume a bunch of data with one CPU instruction. Again, we have the same columnar table, so I'll skip this part. This part is interesting, right? When I was talked about Parquet, columnar representation, then you only care about ID and salary. only these two columns. So only the green patch and yellow patch has to be streamed into RAM, right? And Amit had again in his talk a lot of description about disk is slower, RAM is faster, CPU cache is even faster, and registers are the really fast ones where the instruction actually execute. So you stream things into RAM much better than getting more things from disk. RAM is also expensive, by the way. So you take, this is the only thing you want to compute on. So only salary you can put in cache, CPU cache, and this is a SIMD enabled CPU, by the way. I mean, obviously this should be a huge thing. For the illustration, I have put it just 2 and 2. It should be at least 1024 or something in a go. So you take 2 of them, put it in the register, and execute the CPU instruction on both of them. And imagine like 1024 of them, right? One group of 1024 greater than 15,000 of salary, you will get it a bunch of values in return where everything in that block is greater than 15,000, right? And then you have the other concept, right? The other one you can just move from CPU cache to register, right? If you can use CPU cache in a very efficient way, it will be much faster, right? Because that's faster than getting it from RAM, right? So by now you see that columnar representation of data in storage and vectorized execution are a match made in heaven when you talk about analytics queries. Okay, we are talking about storage and fetching, and I also established that ClickHouse is really fast. Obviously, there is some indexing logic there, and so I'll describe how does the primary key indexing in ClickHouse look like, and how do you store data, index data, and how does a query go and fetch the data, right? Very quickly. So you create a table. This is regular stuff. So ClickHouse seems pretty natural if you know SQL. Engine is merge tree. We will look at that representation. Primary key is user ID and URL. Order by user ID, URL, event time. Order by means that I want ClickHouse engine, storage engine, to keep data ordered by user ID. Obviously, the same row, other columns have to be there, but wherever user ID is same across a bunch of rows, URL has to be sorted, and the same extends to event time, right? I insert some data set there, and then look at the disk utilization, right? If you go to a data directory and look at it, you have files for every column, right? The column files are in red. The orange is the primary index. I'll open the primary index and show in the next slides. And then you have mark files, right? I'll explain about mark files again going further, right? So we talked about the 3 column files. Now these 3 files are on disk. But what ClickHouse also does is you split the column files into something called granules. Think of it as logical representation where we have offsets that tell me that this bunch. By the way, this is ordered, I told you. So this contains the range of data from this value to this value. This granule contains the data from this value to this value, and like that, right? And all of these are called granules. This is one granule, this is another granule. So we have around 9 million rows in this table, and you have granule 0. So total you have 1083. You have one value for the granule in the primary key. So it's a really sparse primary key. This is 9 million, but primary key, by the way, only has 1083 entries, right? 8192 into 1083, that's the 9 million rows, right? So that's what I say, all the first values. So this is your primary key. This is sorted. When you come for querying, all you have to do is do a binary search on this and try to find the exact granule or set of granules which might contain the data you need, and stream to memory only those disk blocks and stuff, right? Querying I promised you. So yeah, I mean top 10 queries, top 10 clicked URLs for a given user ID. You just do a binary search in the primary key over this value. You find this mark number 176. I just need that granule to get the data for this user. So this table again, at the cost of repetition, has 9 million rows, But how much did I scan? 8.19 rows, right? Why? Because that's the size of one granule that I had to fetch from disk, nothing else, right? The disk block that contains that granule. And I told you that I'll talk about mark files. Mark files, what it does is, once you know where it is in the index, there will be a similar mark file for this column. I go to line number 176 in the mark file, and there I will have the disk offset where the granule is located. Okay. The next thing, apart from indexes, that I want to have is data lake integrations. How many of you have used data lakes? Oh, okay. So spend a bit more time, right? How many of you have heard of Apache Iceberg? Delta Lake? Apache Hudi? Okay, fewer. Okay. So what I want is, if I have to have a analytics compute engine, it should be able to query data from Iceberg tables, hopefully these tables as well, and it should be able to query data directly from Parquet. By the way, Postgres has an FDW, right, foreign data wrapper, to query files from Parquet data. So yeah, what is Iceberg, right? Without wasting much time, if I have to explain it very quickly, you have a bunch of files on the disk, and you want to make sense of what is a table, which data file corresponds to which table, which column, all of that. All of the semantics of what is a table is what is a spec that Iceberg represents, right? So Iceberg is a table format specification. It's a set of APIs and libraries documented as a spec. It's not a storage engine, implemented storage engine. It's not a execution engine. It's not a service where you can just give the URL to somebody, they can make their tables or databases or query something like that, right? What happens is, some engine is implemented as per Iceberg specification, and it is called an engine that can write or read from Iceberg tables, right? I mean, if you don't understand this fully, don't worry. I mean, there's a lot of information there. But what is a database, right? It's very similar concepts in data lake, obviously. You have the object storage, S3 or a similar compatible object storage. Then you have file format. We are saying Parquet here. It could also be ORC. Table format, that specification of what is a table, table UID, where should I go and read the meta for this table and stuff like that. Then you have a bunch of compute engines. All of that follow Iceberg spec, so they can query data in Iceberg. They can also query data in Parquet. I really encourage you to read this white paper called the Composable Data Management System Manifesto. It's almost like I'm obsessed with it. I made everyone around me sitting in office read this. I talk about it often when I talk about architectures, and they ended up reading that. But what it talks of is, there's this concept in this paper saying, you know what, these database, the older databases, if you look at it, they are basically monoliths, right? Maybe Postgres is already evolved on that level when I think of it now, because you already have a table access method, and then you have your traditional storage engine there, and there is a lot of work in the community around, at least around extensions for making columnar storage engine and all of that. And the query layer is used by so many data stores or databases like Yugabyte. If you know that, they use the Postgres query engine. There's a host of places you use Postgres query engine. So basically, decomposable system says that, wouldn't it be wonderful if you had a file format that is really well implemented, and you can use just that for your database, table format specification that is implemented, and you use your favorite one, and assemble all of these to make a database. If you're doing a startup writing a database, maybe you want to innovate in one of these layers first. So just write that from scratch, or fork the library and make some changes. The other layers could just be the most popular implementations of it. But yeah, I mean, if you're looking at a regular database, you give up your storage engine mostly to stick to Iceberg format, because you're implementing this part and you're going over this part, so you don't need an extra storage engine now. So in that sense, it becomes a federated query engine. It can query from multiple places, its own storage engine as well as the Iceberg table. And when I talk of all of this, saying this is the thing I want to see in a OLAP database in 2025, if we are to imagine Postgres as a OLAP engine, it would be really nice, no, if you could have an S3 table and a bunch of Parquet files, and Postgres could just query those, right, with Postgres queries. So this is the line I'm talking about here, and the same about Iceberg, obviously, right? So Postgres should be able to read from Iceberg tables and write to Iceberg tables. And by the way, again, looking at the neighborhood, yeah, what are the other databases or other distributed data systems doing? MySQL HeatWave announced support for Parquet and Avro files. S3 tables, you have a way to store Parquet, Iceberg tables there. I talked of ClickHouse some time earlier now, and they are able to read Iceberg tables. They are working on adding support for writing to Iceberg tables. That's in their 2025 roadmap. And DuckDB also can read. On write, they can do some stuff, I think, and they are working on adding better support. Lastly, I think Peter in his keynote today also mentioned this, something around this. So you probably would think that there's a huge data set and you want to distribute it over multiple nodes. So you need to have some sort of sharding logic in the database if you are to work with analytics system. Well, maybe not on the first day, because this is a really popular blog, right? I couldn't find a better way to represent this. You look at the number of customers that has huge data set, it's really tiny, right? Look at the graph, right? On the right, there is a blog from Fivetran where their CEO talks about, so basically they move data from Postgres and other stores to Snowflake, Redshift and all of that. The 99th percentile query scans just 300 GB, right? So the queries in analytics database don't actually go and touch so much data. The storage obviously has, but like I described in the ClickHouse indexing, you have to reduce the amount of data you touch on disk. And the other part that Peter I referenced for, right? The definition of big data, if you look at it in 2006, it was like big data is what cannot fit on a single node. Since then, single node has come a long way. You can have really big disks, and you can have RAMs that are in excess of 200, 300 GBs, right? So you can fit all that data you want in querying in the RAM. And these are affordable. It's not the biggest machines on S3 today, right? So I talked about all these concepts, right? Columnar, vectorization, Iceberg support, Parquet support, indexing, distribution, all of that, right? So let's look at a few indexes on a bit higher level, but if you have questions, I'm happy to answer those. And then how are these extensions made? By leveraging onto the rich ecosystem of Postgres. You have extensions where you have newer data types and stuff. You have foreign data wrappers and you have table access methods. So you know of extensions by now, I think. PGDuckDB is an extension for Postgres. ParadeDB leverages foreign data wrappers to get data from S3. Basically, they push the predicate there, get only the relevant files and all of that. Otherwise, there will be too much in the network flowing through, and then stream that in the DuckDB query engine to use their vectorization. And then you also have these couple of projects, PG Mooncake and Hydra, that are also working on extracting data out of columnar storage and or even data stored in regular Postgres, and providing it to DuckDB for using its engine, right? So by the way, I talked about Postgres a lot earlier. This is from the benchmark, and we committed, we added one of these, I think. So all of these databases are Postgres plus DuckDB extension, and this is the most tuned Postgres. Look at the difference, right? If you could just query Parquet, it will be much faster with vectorized execution. What is happening in the ecosystem, right? I was toying around this idea, and then I thought, last 8 months, 4 extensions, and all of them are sort of coming from some vendors, some companies, right? Crunchy Data first, in my research, announced a proprietary bridge that sticks in DuckDB inside Postgres extension. Next month, ParadeDB announces PG Analytics. 2 months later, DuckDB Labs, the folks behind DuckDB database, they announced that they are working on making an extension based on DuckDB inside Postgres. And then couple of months, you have Mooncake, PG Mooncake, right? So a lot of activity. and I was basically very happy to see again, to reference Amit's talk, that he's already thinking about the executor to see how we can leverage SIMDs in future. So I mean, if there is any help I can do there, I am leading to sort of doing some research there. I'd be happy to do that, right? So and by the way, you would ask, why are you raving about DuckDB all the time? Why are you not talking about other computers that can do similar things in memory analytics? CSDB is not probably as well marketed, but it's really good product, right? And this is ClickHouse benchmark, so let's trust them, saying their own thing is slower than DuckDB, right? But then it is just a ridiculous argument that some database is slower. I mean, it's not one standard query that works for everyone after all, right? And then you have data fusion, which is getting really popular, works really well with Apache Arrow and Parquet. And DuckDB, by the way, has a lot of features as well. Really popular, permissive license, a lot of features and all of that. So yeah, maybe this shows you. This is some feedback from Crunchy database folks who made that DuckDB based bridge, and they are really happy with DuckDB engine. So I promise that we will be back to answer these questions. Let's go, right? So just one slide on DuckDB, right? Embedded in memory analytics engine. So this is what we leverage to put inside Postgres extension. Optimized for single node execution, and single nodes can be big, right? So we can sort of slice and dice a lot of data. Columnar format for efficient storage. These are the features of DuckDB. This is just DuckDB, not PGDuckDB, right? So not the extension, the full database. Columnar format, vectorized execution, can persist data on the same node that you are running DuckDB on, can read Parquet and Iceberg on S3, and if you need a hosted DBAS and all, you have MotherDuck, right? That provides DuckDB as a service. So we listed all of these things. We talked about them. If you look at this combination now, they work really well together, right? Like we can pretty much tick all of them. Storage is the only thing you would question, but let's assume that storage on single nodes, the single nodes can store a lot of data and do a lot of compute these days, right? So if you now think of PGDuckDB, this is done by folks at DuckDB Labs and the Hydra DB. Hydra is a organization as well, which is backed by, which was in one of the Y Combinator batches last 2 or 3 years ago. So what you can do with DuckDB is you still have the data in Postgres. Your product manager suddenly came in the small startup case we talked about and asked you for analytics and all of that. Put a DuckDB extension, let it read data from Postgres, uses SIMD enabled vectorization and stuff to query data for you, and you can do slice and dice there. If you have a lot of things to do there and you don't want to disturb your Postgres, copy that data in a Parquet format and do as much analytics you want. It will be really efficient, right? And the duck can swim through the lake really well, right? You see all of these functions that DuckDB is sort of able to execute. Read Parquet, read CSV, read JSON, Iceberg scans, basically reading from Iceberg, scanning the files there and stuff like that. The last one is Delta. This is the one that Databricks helms, the thing similar to Iceberg table format, right? How does PGDuckDB execute queries, right? You have a bunch of ways. In a session, you can say force DuckDB execution. So DuckDB will take over the Postgres query. If the query contains a function that's a DuckDB function, then it will forward it there. If it contains a columnar table or something that is stored by DuckDB, or in the mother duck, you can extend that there as well. Then it will query from those tables. If it is a Postgres tables, it will query Postgres using its own. So DuckDB has a Postgres extension as well, right? So they leverage that. If you force DuckDB query execution, then after the planner, it will sort of branch off from the executor hook and take its own path in the DuckDB code base. It's a PGDuckDB code base. This is the next database that I talked about. What they do is they make one more columnar storage engine behind the table access method, right? So you create an extension. This is normal stuff, I think. You create a table. We call this example table heap table using heap. This is your regular Postgres table. And you can create columnar table using columnar, right? This is a new thing. And then you can execute your regular Postgres commands. This is the list of tables, and you have your access methods here that tell you which kind of table it is and stuff like that. And a really cool use case I found on their docs or in demos is you can store the old partitions of a row-based table inside columnar and all of that also. When you make partitions, you can say that I want to use columnar engine. So you can slice and dice on your old data as if it was a columnar store. ParadeDB, I talked about it a bit earlier. It uses the foreign data wrappers. So foreign data wrapper of S3 and Parquet that goes gets the right columns from Parquet data, streams it into DuckDB execution engine inside Postgres extension, and it can query via DuckDB again table formats like Iceberg or Data Lake, right? Again, I have the sort of example source code here. You make a FEW kind of command, you sort of you know all of that, right? So after this block, it will start working like a regular Postgres foreign table. And the last one, PG Mooncake, right? Again, to very quickly go through the commands, you create the extension, you create a table using column store. So this is their implementation of the columnar storage behind the table access method of Postgres, and then you do regular Postgres stuff, insert, select, and whatever, right? It also uses DuckDB execution inside the extension. At this point, it is repetitive, I think, right? So, but yeah. PG Mooncake basically is more focused around getting data from S3 and Parquet files and all of that. You can have Parquet files in local as well. There's a wonderful demo that I think I didn't link to, but you can find on the NeonDB docs, because NeonDB comes with a PG Mooncake extension. You can play around there. And all of these things that I discussed, I touched a lot of things. So I assumed that for some things people will be wanting to go deeper and stuff like that. So me and my friends who are sort of working on all of these, we have a GitHub repo where we are putting in detail every sort of research that we do. So we have regular MD files where we put everything. If you want to join on this journey and sort of be part of it, this is what we intend to do next. We're working on optimizing Postgres for OLAP on ClickBench dataset and queries. We want to do the same for other famous analytics database datasets and queries. Then we note down our best practices in this GitHub repo, which is the QR you see here for. And then I have a few bugs that I have found in the extension, the 4 extensions that I just talked about. So if you want, I can list down the queries in the GitHub, and you guys can take a stab at fixing those queries. Like just a couple of 2-3 nights ago, PG DuckDB new version announced support for using Postgres indexes, right? So these databases, now you understand, are very, very nascent stage. It's easier to go and sort of do contributions. There is a small team, they need contributions right now, right? Any questions? Please. Yeah, please.
So you have done a lot of research on extensions that you have just explained here, and plus you have done benchmarking. So which one is the best out of all that you have used?
Oh, I had a slide. I removed it.
So you put that
yes.
DuckDB alone, which is like a separate database, but not an extension.
Yes.
The extension is different, which is PG
Yes.
underscore DuckDB.
Yes.
Right? In extensions, basically, like Moon, Cake, and
yes. So it depends on your use case. If you have a bunch of data already there in Parquet, you want to use PG Mooncake, right? If you want to use a table you use a database which gives you a table access method where you can use it like a hybrid database, some tables in row format, some tables in column format, then you can use Hydra, right? If you have database in Postgres and suddenly you want to just query from there only, you don't do a copy and stuff, very ad hoc, you can use PG DuckDB, right? I have an extensive MD file in the GitHub repo. GitHub repo is not here, but you can see that, yeah.
Second question on that Snowflake versus this, right? There's no clear understanding how much data you are querying in Snowflake.
So it's 100 million rows in both of them.
But in size?
So I mean, it's the same data inserted in both of them. Postgres, it takes 70 GB. Tuned one takes around 120, 130 GB. Snowflake can store it around in 12 GB, right? But the same data is pushed to all of them, right? I will be around, so you can ask me more questions. Maybe 1 or 2 I can take. I don't think these are operationally used a lot right now. You will have to try that. I don't think somebody has put it on the cloud and tried it. Anyway, AWS validates its extensions and all of those mostly, so you'll have to probably wait. But your own Postgres, you can use this. These are very early projects right now, but they should get there, I think. Yes. Mm-hmm. Mm-hmm.
But afterwards, it seems like for OLAP, we are changing the storage layer, we are doing a lot of changes that going back. So now it seems like the OLAP solution will be.
So it's like you have a table where you want to store data in row format, and that is your transactional table. In the same database, you can make one more table. Maybe clickstream or something can stay in the columnar representation. In the application, you can query that part when you do want to do analytics or something like that. Yes, your applications, codes, everything doesn't have to change when you want to move to an OLAP store or something, right? Queries are same, right? Yeah. Any other questions? Or we can. I'll be around, or you can ping me on LinkedIn. Yeah. Thank you. Sorry?
Very informative and
Not
cute
yet.
session, Shivji.
Any specific reason of not including time?
Timescale is already part of ClickBench. You can see timescale there already. So I did not just present it here because I already.
More or less it ticks all the